Alyssa, thank you so much for that reminder. Welcome, everyone. Thanks for coming. Happy Monday. I wanted to let you know that of where we are and where we're going, okay? We're looking at reactions in stoichiometry right now in this chapter. In the next chapter, we'll be looking at solutions and then reactions in solutions, right? So we'll carry on this theme. And then after that, we're going to gases. We're going to learn a little bit about the properties of gases, the laws that govern them, and then reactions also in gases, right? So that's kind of where we're heading in the next couple weeks. And then, of course, we'll have another exam. And if you can believe it or not, this is week 6 of 15 of this course, right? Which means that you guys are 1/3 of the way through. Can you believe that? Pretty crazy, but it's gonna go fast, I know. All right, let's talk a little bit about these concepts: limiting reactant, theoretical yield, and percent yield, that are super important when discussing chemical reactions. You saw the video, I hope. Raise your hand if you've seen the video already before class. All right, so you saw the video on this topic, limiting reactant, theoretical yield. Remember in that video, I was trying to draw a parallel, right, between a pizza recipe, right, and a chemical reaction, yeah? And so this is the pizza recipe. When I was a kid, I used to make pizzas on English muffins. And my family we just didn't have a lot of, well, we had some junk food around. And so we would do an English muffin with Cheese Whiz, right, for the cheese, and ketchup for the tomato sauce, if you can believe that. And then we'd put it in the toaster oven and, you know, we'd make our own little mini pizzas. They were terrible. But anyway, this is much better. We use a real pizza crust, 5 ounces of tomato sauce, 2 cups of cheese. You make your pizza, right? So my question now is, what if you had, 4 crusts, 10 cups of cheese, 15 ounces of tomato sauce? How many pizzas do you make, right? So those are all the ingredients you have as you go through your cupboards. And this recipe determines the relationships between the different ingredients, right? Just like a chemical equation tells us the relationship between the different reactants and products, right? The stoichiometric relationships, all right? So from the 4 crusts, right, you can see you can make 4 pizzas, right? Because you got 1 crust, 1 pizza. So if you have 4 crusts, you get 4 pizzas. If you have 10 cups, you can figure that out. You make 5 pizzas, 15 ounces of tomato, right? Only makes you 3 pizzas, right? So, sorry. So, the tomato sauce is what we call the limiting reactant, right? It's the thing that limits how many pizzas you can make, all right? So these same principles apply to a chemical reaction, right? So again, you already saw the video, so I'm not gonna go through it, but we're gonna work some examples, but let me just put forth the definitions of all these things so you have them in your notes, okay? So first of all, the limiting reactant, right? So again, when you have a chemical reaction, the equation tells you the relationship between the amounts, right? But that doesn't necessarily mean that those are the things you put together in the beaker in those exact relationships, right? Just like you may not have the exact relative proportions of the different ingredients needed to make pizza, right? And so you're going to be limited by one of the ingredients. The same thing happens in a chemical reaction. So the limiting reactant is the reactant that is completely consumed in the reaction, right? And it limits the amount of product you can make. Right? So in this case, because the tomato sauce only resulted in 3 pizzas, right? It was the limiting reactant, right? It limited how much pizza we can make, all right? So that's limiting reactant. The reactant in excess, is any reactant that occurs in a quantity greater than is required to completely react with the limiting reactant, right? Any reactant present in a quantity greater than is required to completely react with the limiting reactant. So here, right, because we have 10 cups of cheese, that's more than enough to react with, to make the pizzas with the 15 ounces of tomato sauce. So that's in excess, right? Similarly, the crusts are in excess, right? Because we have enough crust for 4 pizzas, but we only have enough tomato sauce for 3. So this is in excess. So in this set of initial conditions, right, if we have these conditions and this is a limiting reactant, the cheese is in excess and the crusts are in excess. Does that make sense? Okay, then we also have the theoretical yield. The theoretical yield is the amount of product that can be made based on the limiting reactant, right? The amount of product that can be made based on the limiting reactant. Right, so in this analogy, right, the theoretical yield is 3 pizzas. Theoretically, with the reactants that I have, I can make 3 pizzas, right? So that's the theoretical yield. Now, you don't always get the entire theoretical yield, right? Even when you're making pizza, right? Because let's say, you know, you put the pizzas in the oven and you accidentally put one on the bottom shelf too close to the burner and you don't preheat your oven, so the bottom pizza burns, right? So in fact, instead of getting your theoretical yield, you get your actual yield, which is only 2 pizzas in this case instead of 3, right? So the actual yield.
How do you know what the theoretical, or no, the actual yield is when you're doing it on paper?
Great question. So the actual yield is tied to when you actually carry out the reaction, right? Just like, you know, in this case, the amount of pizzas you actually get will depend on how it goes when you're making the pizzas, right? Similarly, the actual yield kind of depends on how it goes when you're carrying out the reaction, all right? So you wouldn't know that unless you're in a problem. You'd have to be told that, all right? Okay, so the actual yield is the amount of product actually produced. Right? So in our pizza analogy, right, if you burn one of the pizzas and you produce only 2 of them, then the actual yield, instead of being 3 pizzas, would be 2 pizzas, right? Theoretical yield would be 3, but the actual yield would only be 2. And then lastly, the percent yield, which is equal to the actual yield over the theoretical yield times 100%, right? So in our pizza analogy, if the theoretical yield was 3 pizzas, but we actually only got 2, right? Then the theoretical, the percent yield, sorry, would be 2 pizzas divided by 3 pizzas times 100%, so it would be 66%, right? Our percent yield, we got 66% of the possible amount of product. Does that make sense? So I really want you to understand this conceptually, and that's why this pizza analogy is kind of helpful. You get the concepts. Really, the chemical, when you apply it to the chemical reaction, it's exactly the same thing, right? There's no difference. It's not any more complicated than this pizza analogy, okay? The only difference is that in chemistry, right, oftentimes amounts are given in grams, right? But when you compare the different reactants and products in a chemical reaction, you always have to compare them in what units? Moles, right? Because a balanced equation is not between grams, but between moles, right? So when you have an equation like this, it's between moles, okay? So this is equivalent to finding everything in moles. Okay, let's just do a couple of questions here. Let's go ahead and start with this one. Let's see if you get in this. So go ahead and try to answer this question. Okay, I'm going to give you a little hint about how to work this out. The best way to work this out is to start off with the beginning amounts of each one and convert to moles of product and see which makes the least moles of product, right? Because if this is kind of like this problem, right? You have 4 crusts, 10 cups of cheese, 50 nuts, and tomato sauce. How do we figure out what the limiting reactant was? We said, okay, if I have 4 crusts, how many pizzas can I make? If I have 10 cups of cheese, how many pizzas can I make, right? If I have 50 ounces of tomato, how many pizzas can I make? The one that made the least amount of pizza is a limiting reactant, right? So you would want to do the same thing here. If I have, so you look at, it says red circles. So I have 1, 2, 3, 4, 5, 6, 7 red circles. So I have 7A, right? And then according to the balance equation, what's the relationship between A and the product? It's what? In other words, if I want to convert this to moles of product, what should be my ratio here?
It's 1 to 1.
It's 1 to 1, exactly right. 1 AB2 divided by 1A, right? So then this cancels, and how many AB2s do I get? I get 7 AB2, right? 7 particles of product, right? If I do the same thing for B, 7B times, what's the relationship for B now from the balanced equation?
A 1 to 2.
It's 1 to 2, right? So how would I write the conversion factor?
1 AB2 and then divided by 2B.
Exactly right. 1 AB2 divided by 2B, right? So now my B's cancel, and notice how many AB2s I get. 7 halves AB2, right? So in other words, I have enough of A to make 7 AB2s. I have enough of B to make 3 halves AB2. So which one is my limiting reactant?
B.
Pardon me?
B.
B, right? This is my limiting reactant. Right? B is the limiting reactant. Which is the reactant in excess?
A.
A is in excess, right? I have more than enough A to react with the amount of B that's present, right? So that's why it's in excess, yeah? Does that make sense? So what's the right answer here?
B.
It would be B.
B, okay. A lot of you, a good number of you put A, right? So that's why I kind of worked it out for you here, but it's definitely B, okay? All right, good. Are there any questions? Does that make sense? So again, the principle is this. If you're figuring out what the limiting reactant is, right, just figure out how much product you can make from each of the starting materials, and the one that makes the least amount of product, right, is the limiting reactant, okay? And everything else is in excess. That's the way you do it, okay? Okay, so now the limiting reactant determines the amount of product you can make, right? Determines the amount. So when you're calculating the theoretical yield, right? You base that on which of the reactants, the limiting reactant or the one in excess, right? Go back to our pizza. When we were figuring out what the theoretical yield of pizzas was, we determined that based on what?
A limiting
Your
reactant.
limiting
Limiting reactant, right? The amount of pizzas made by the limiting reactant. So it's the same thing for a chemical reaction, right? You base it on the limiting reactant. So let's do a full problem here, and then you'll have a chance to do one, okay? All right, so here we go. Let's set this up as sort of like the way I've showed you how to set up problems. Given, so you're given, because sometimes, you know, it's nice to just get everything down on paper. Again, if you start staring at a problem, you don't know where to begin, start this way, right? What's your starting point? What's your end point, okay? So I'm given 9.05 grams of ammonia, right? And it says that it reacts with 45.2 grams of copper 2 oxide, right? And I have the balance equation there. And then I want to find the percent yield. All right. Oh, and it produces. Sorry, you're also given that it produces 4.50 grams of what is that? It actually produces 4.50 grams of
Copper oxide.
No, it is. I should have written this in here. Nitrogen. Sorry, 4.5 grams of. Let me just jump in here and fix that. 4.50 grams of nitrogen. Yeah. So, how many grams of nitrogen can be made from 9.15? Blah blah. If the reaction produces 4.5 grams, what is the percent yield? So I want to find the percent. I want to find, first of all, how many grams of nitrogen can be made. That's the what? Theoretical yield. Right. Notice I'm interpreting the problem here as I write down my given and find. Right. I want to find the theoretical yield, and then since I'm given the amount that's actually produced, I also want to find the percent yield. Oops. I want to find the percent yield. Okay. So there's our problem setup, right? So what am I going to do? Okay. Well, here's my starting materials, right? These two things are kind of like the amount of the different parts of the recipes that I have, right? I have 4 across, 10 cups of cheese, and 15 ounces of tomato sauce, right? In this case, I have 9.05 grams of ammonia and 45.2 grams of copper oxide, right? Those are my starting materials, yeah? Kind of like in the pizza analogy, what these things are over here, okay? And I'm trying to find the theoretical yield. I'm trying to figure out, okay, how many pizzas can I make? In this case, though, it's not pizzas, right? It's a chemical reaction, right? So it's how much nitrogen can I make, right? How much of this can I make, right? So what should I do? Well, what did I do with the pizza analogy? I calculated how many pizzas I can make from the amount of each of the starting materials, right? I said, okay, if I have 4 crusts, I can make 4 pizzas. If I have 10 cups of cheese, I can make 5 pizzas, and so on. So what I'm going to do is I'm going to start with each of the materials that I have, and I'm going to figure out, okay, how many grams of nitrogen can I make from those things, right? So I'm going to say 9.05 grams of ammonia, right? And I'm going to say, how much nitrogen can I make? And I'm just going to, so this is just, so at this point, it's a stoichiometry problem, right? If I have a certain amount of ammonia, how do I figure out how much nitrogen I can make from that? What's the series of steps?
Do you go from the molar mass of ammonia to moles, and then you use the equation as a conversion factor?
Yes, exactly right. That's exactly right. Thank you. So 1 mole over 17.03 grams, right? That gets me to moles of ammonia. Now I can use my balance equation, right? The recipe, yeah? I can use the recipe to give me the relationship between moles of ammonia and moles of nitrogen, right? And what's the conversion factor there? How should I write it?
1 nitrogen
1 mole nitrogen, yes.
over 2 moles of ammonia.
2 moles of ammonia. That's correct. Okay, that's exactly right. So, so the moles of ammonia cancel out, and now I have moles of nitrogen, right? And so that comes out to be 0.266 moles of nitrogen. Does that make sense? Awesome. Okay, then I'm going to take the other starting material, my copper oxide, right? And I'm saying, okay, how much nitrogen can I make from that? 45.2 grams of copper oxide. And I'm going to do the same thing. Notice grams to moles. I'm not converting to grams yet because I don't have to yet, right? First, I'm going to figure out which one's limited, and then I'm going to convert that to grams, okay? So I'm going to go grams. I'm going to convert that to moles. The molar mass for copper oxide is 79.55. So 1 mole over 79.55 grams, right? And that's going to cancel, okay? Then I need a ratio, right, that comes from the balance equation. What's the ratio for copper oxide? Is it the same as for ammonia?
No.
No. What's the ratio? What's the correct ratio here?
1 to 3.
1 to 3, right. 1 mole of nitrogen, right? 1 mole of nitrogen to every 3 moles of copper oxide, right? I get that right from this balance equation, right? You like my little laser pointer? 3 moles of copper oxide. Okay, 3 CuO. Yeah? So that's going to cancel that. Now I got moles of nitrogen again, and now I find that I get 0.189 moles of nitrogen, right? So let me move this over a little bit so you can make sure I can see it all. Okay, so notice I have ammonia to make 0.266 moles of nitrogen. I have enough copper oxide to make 0.189 moles of nitrogen, right? So what is my limiting reactant?
Copper oxide.
Very good, exactly right. So this is my limiting reactant. Right? My limiting reactant is the 45.2 moles of copper oxide. And then this is my theoretical yield, but right now it's in moles and I want to find it in grams, right? How many grams of nitrogen, right? So I'm going to go 0.189 moles of nitrogen, right? Times 28.02 grams per mole, right? That cancels out, and I get 5.30 grams of nitrogen. And this is my what?
Theoretical.
Your actual yield?
That's on my actual yield.
Theoretical.
That's the
Or
theoretical
your
yield.
theoretical?
Yep, that's my theoretical yield.
So is your actual yield 4.5 grams of nitrogen?
Correct. 4.5 grams of nitrogen is what was actually produced when we carried out the reaction. That was given right here, right? If the reaction produces 4.50 grams of nitrogen, what is the percent yield? Does all that make sense?
Yes.
Okay, good. Glad to hear it. All right, so now I have my limiting reactant. I found the theoretical yield, right? My last thing now is to find the percent yield, right? So the percent yield is going to be equal to what?
4.50 grams divided by 5.30.
Right? 4.50 grams of nitrogen, right? What's that? That's my actual yield. Right? And I'm going to divide that by the theoretical yield, which is 5.30.
And then time 100.
Correct. Exactly right. Thank you. So that's my theoretical yield. Right? And then I'm going to multiply by 100%, right? And that's going to give me my percent yield, 85.0%. That's my percent yield. So the percent yield should always be less than 100%, right? It would be, if you get a percent yield that's more than 100%, something went wrong. Yeah? All right, something went wrong in working out the problem. It should never be over 100%. You can't make, right, it would be like saying, oh, I have all these ingredients, right? And I ended up making, 10 pizzas, right? It's not going to happen, right? The theoretical yield limits the amount of product you can make. So the actual yield is never going to be more than the theoretical yield. It's always going to be either the same or less. Okay?
Can you be given the theoretical yield and try to find the actual yield?
Only if you were given the percent yield as well. Right? If you're given the percent yield and the actual yield, you could figure out a theoretical yield that way. But this kind of problem that we just worked through is a very typical Gen Chem kind of problem, right? You're going to see a problem like this on the exam, I promise you, right? So, so make sure you know how to do this kind of problem because it involves stoichiometry, it involves knowing all these principles. All these principles are super important in all your later chemistry, right? As you do reactions and carry out reactions in organic chemistry and inorganic chemistry or wherever, right? Super, super important concepts. Emily.
Is it standard that you would convert the theoretical yield to grams, or will it sometimes be in moles, and will the question specify that?
It depends on the question, but normally if they just ask, like in this case, they did say how many grams, right?
Right.
So typically that's what you want because in lab, what do, right? You carry out the reaction and then you weigh it, right, to see how much you have, right? So that's the typical kind of problem. But you know, you could do it. I mean, it could be done in moles. Like here, we're kind of dealing in just dots, right? But you could deal in moles, but more commonly, it's going to be grams. Good question, Alexander.
Yeah. So I'm kind of used to being only given the masses of the reactants, and then using one of the products to compare everything to. So if I'm given some gram or some mass from the reactants and from the products, I just choose one of the ones that is not given to determine what their limiting is.
Yeah, so there are other ways to do this. I personally think conceptually, the easiest way to do it is to do it kind of like with this analogy. Figure out how many products you can make from each of the reactants, and then the one that makes the least is the limiting reactant. I just think that's the easiest to understand conceptually. You could do it a different way. You could say, okay, how much tomato sauce would I need to react with 4 crusts, right? So you can say, okay, with 4 crusts, you can figure out how much tomato sauce. How much tomato sauce do I actually have? Oh, I actually have less than the amount needed to react with 4 crusts. Therefore, that's my limiting reactant, right? So you could do it that way as well, all right? But I just think conceptually, this is an easier way to do it.
Okay.
And since most of the time you'll be figuring out how much product you have to make anyway, you might as well just do it this way.
So you could easily have just compared everything to the water, I guess?
Just to each other. So I could have said, all right, how much copper oxide do I need to react with ammonia, right? And then I could carry out that calculation and I could see if I had that much copper oxide. And if I did, if I had more than that amount, then I know that ammonia would be my limiting reactant. If I had less than that amount, then I would know the copper oxide. So you could do it that way as well, and that's totally fine if you want to do it that way. I just think conceptually this is a little bit easier to understand. And since you always got to figure out the amount of product anyways, most of the time, you might as well just go all the way.
But wasn't the other product that was not given water in the last problem?
Correct.
So couldn't you have compared it to that instead
Sure,
of
you could have said, yeah, because notice, oh, very good question. Whatever is the limiting reactant for any product is the limiting reactant for all products. Yeah?
That makes sense, yeah.
Let me write that down so you guys get that in your notes. Limiting reactant for any one product is the limiting reactant for all products. Okay, that's always going to be the case, right? Because if the amount of, like we found here, right? If the amount of copper oxide limits how much nitrogen I can make, it's also going to limit how much copper I can make and how much water I can make, right? The theoretical yield depends on which of these products you pick, right? And that just depends on what you're doing, right? So in this case, the problem was asking for nitrogen, right? But it could have easily have asked for water, in which case, you, instead of converting to nitrogen here, what would you do?
Convert to water.
Correct. Right, you would just convert to water. Okay, good question. Any other questions? So I'm gonna have one here for you to do. Again, it's a little bit of a time-consuming calculation, so it's gonna take you a few minutes to work this out. I'm tempted to try what we tried before, where we broke out into breakout groups, so you can talk amongst yourselves a little bit and compare. Last time that was a complete disaster, partly because you didn't have the problem. So let's try this. I'm gonna give you a minute to write down the problem. And then we'll go to breakout rooms. You can work it out. And then we'll come back, and I'll make sure to unmute myself this time so that you can hear me, and we'll discuss it. Does that sound like a good plan? Again, another experiment. We'll see if it works. I'd like you to be able to talk with each other a little bit. So what do you think? Is it worth a try? Give me a thumbs up if you think it's worth a try.
I'm taking a photo of the problem with my phone, so that might be a good tip.
Sorry, say that again, Taylor.
Oh, I'm taking a photo of the problem with my phone.
Okay,
so
yeah.
I can go back to it.
Take a photo of the problem with your phone, or just set it up, right? You can copy down really quick, and you can say, okay, you can write down the equation. Right, there's your equation. You can write given and find, right? You can set it up. So what mass of ammonia? So I want to find grams of ammonia, right? Could be produced from 15 kilograms. So I'm starting with 15.0 kilograms of hydrogen and 15.0 kilograms of nitrogen, right? So it's saying, okay, I have a certain amount of this, a certain amount of this. How much of this can I make? Okay? So again, what it's basically asking you to find is, okay, what is the theoretical yield of ammonia based on these starting materials? So what's the first thing you have to find? The limiting reactant, right? You have to find the limiting reactant to see which one limits the amount of product, okay? I see some little discussion here about the limiting reactant is for all products. Yes, once you find the limiting reactant for one product, it's the limiting reactant for all products. Okay, here goes. We'll try this. Are you guys ready? Got it copied down? All right. Hope this works. I'm going to do 3 people per room, and here we go. Hey guys, did I blow it?
No, I don't think so.
Okay.
Is this breakout room working?
I think so, yeah.
But there's 20 people in here?
Yeah.
I guess.
I think you ended up setting it
We
to
have to make
3 breakout rooms instead of 3 per room.
Yeah, that's what I did wrong. Okay. I'm getting there next time. Go ahead and work on this, and you can talk a little bit together, but it might be kind of hard. But go ahead and try. Thanks.
Hi, Tro. You're muted again.
Got it.
I'm like, this is like, I'm having the most trouble with this type of thing. For me, like breaking it down so into like just, instead of like using the equation or like the different, like the actual symbols, like the H2 and the N2,
Yeah.
could you write it as like A plus B equals like, so like instead of like using that, because I program a lot, so that kind of makes more sense to me when I reckon.
I don't think any problem with that, as long as you remember what each symbol stands for, sure.
Yeah, but could you do that for me so that I can see, like, because I don't understand where everything's supposed to go. That's my problem.
Stick around and we'll look at that after class, okay?
Okay, all right, thank you.
Professor, can you share the question again, please?
I can't do that while we're in the breakout room, so that's why I asked you to write it down.
Okay, yeah, okay, no worries.
Yeah, I can't do that.
I guess so.
Guess so.
Wait, I have a quick question, Troy.
Okay, yeah, go ahead.
Wait, why isn't it just I guess 30 kilograms of ammonia?
Why isn't it just 30 kilograms of ammonia? Oh, right. No, because you got to convert to moles, right? The relationships between the reactants and products have to be in moles, not in grams, right? So in other words, if you have 10 grams of hydrogen, you can't just say, oh, okay, it's a 3-to-2 ratio in terms of grams. You got to go to moles first.
No, I'm saying if you got 15 kilograms of H2 and 15 kilograms of N2, wouldn't the product just be 30 kilograms?
Oh, great question. Okay, very, very good. Let me explain that really quick, right? So if I have 4 across, 10 cups of cheese and 15 ounces of tomato sauce, can I just add that together to figure out how many pizzas I'm going to make?
No, but that will give you the amount of mass of what you're going to make.
Right, but I can't make that many pizzas, right? Because this isn't together in the right stoichiometric quantities required to make pizza, right? So in other words, I have too much cheese. I'm not going to use all the cheese, right? I'm not going to use all the pizza crust. So the total mass of the product is actually going to be less than if you sum up the masses of the reactants. Does that make sense?
Wait. So the total mass of the product is going to be different than the mass, the sum of the products, of the reactants, I mean?
Yes, because not all of the 15 kilograms of this and the 15 kilograms of this are going to react. Let me do the problem, and then you'll.
Oh, I got it. I got it now.
Okay.
Okay.
Okay. I'm glad.
Okay, that makes sense. Thank you.
All right. Well, I'm sorry to have made the breakout rooms too big. All right. So at least it wasn't as bad a disaster as the first time, but still pretty bad.
I have a question.
Yeah.
Since here it's asking for just grams for the mass of ammonium, we're just supposed to find the limiting reactant and then convert it to the grams, right? And that would be our answer?
Correct.
Since we're not asked to find the percent yield?
Correct.
Okay.
In this case, you're just trying to find the theoretical yield. Okay, so let me just work it out real quick. Well, actually, let me open the poll just to see what you guys got before I work it out. So just plug your answer here into the poll. And maybe you're still working it out. I don't know if I gave you enough time or not. But go ahead and plug in your answer here. Oh, nice. Okay, most of you are getting this. That's great. So what you do, 15.0 kilograms of nitrogen times. Now in this case, I gave you kilograms, right? And I want the answer in grams, and might as well just convert to grams here, right? So I'm just going to go times 1,000 grams per kilogram. And that's going to cancel. And then I got to convert to moles. 1 mole over 28.0 grams. And that's going to cancel. Now I have moles of ammonia. I'm trying to get to moles of NH3. Again, the very important conversion factor here between the two. What was it? What is it? What's my conversion factor here between moles of nitrogen and moles of ammonia? How should I write it? What goes on top?
That's going to be 2 moles of ammonium over 3
2 to
moles
1
of hydrogen.
2 moles of ammonia over
1 mole of.
Correct. 1 mole.
Oh no, that's it.
Right? That's the ever important conversion factor that comes from where? The balance equation. Right? So if I carry that out, and since it's already asking me for grams, I'm just going to go all the way to grams because I can do that as well. I'll just show you a different way to do it than we did it before. 17.0 grams per mole is the molar mass for ammonia, right? This cancels and that cancels, and I get the answer here in grams, 1.82 times 10 to the 4th grams of ammonia. When we did it before, I just stopped at moles and then converted the limiting one to grams, but here, I'm just gonna go all the way to grams, just as easy, okay? And then for the hydrogen, 15.0 kilograms of hydrogen, again, I'm gonna convert to grams, right? That cancels. And then I'm going to convert to moles. 1 mole over 2.02 grams. And that cancels. Now I got moles of hydrogen, and now the ever important conversion factor from the equation, right? What should my conversion factor be here? Anybody?
2 moles of ammonia over 3 moles of hydrogen?
Exactly. 2 moles of ammonia over 3 moles of hydrogen, right? Again, why? Because for hydrogen, the coefficient is 3. For ammonia, it's 2, right? So I just take that ratio right from the balance equation, right? And again, the hydrogen cancels, right? Now I got moles of ammonia. I'm going to convert to grams. 17.03 grams per mole, right? And I get 8.45 times 10 to the 4th grams of ammonia, right? So I have enough nitrogen for this much ammonia. I have enough hydrogen for this much ammonia. What is my limiting reactant? The nitrogen or the hydrogen?
The nitrogen.
The nitrogen, right? That limits the amount I can make, right? So the amount of product that I can make from the limiting reactant is the theoretical yield. All right, so the theoretical yield here is 1.82 times 10 to the 4, right? What mass of ammonia could be produced, right? That's the maximum amount that could be produced. Does that make sense? Okay, looks like most of you got that, so good job. Any questions on this super important principle that you're going to see over and over again? Does everyone understand it?
Well, I got a quick question.
Yeah.
What exactly happens to the excess in chemical reaction?
Oh, great question. What happens to it? It just sits there in the beaker. So let's suppose, let me draw you a picture here, right? So initially, here's your beaker that's reacting, right? And let's say this is the nitrogen, right? And let's say this is the hydrogen. You have tons more hydrogen, right?
Yeah.
So then you do the reaction, and then let's just say that, I need one more color. So let's say the blue is the ammonia. So I'm going to get the blue. Now, I'll ask you this question. There's going to be some other dots in here. What color are they going to be? Remember my color scheme. Let's see if I can remember it. Red was hydrogen. Red was hydrogen. Black was nitrogen, right?
Yeah.
So there's going to be one other kinds of dots left in here. What are they? Are they going to be black or red?
Red.
Red.
Red, exactly right. Any black dots?
No.
No, because that has been all used up, right? So your answer to your question is what happened to the extra hydrogen, right? It just sits there and never reacts, right? Only some of the red dots react. It's kind of like saying, oh, what happens to the extra cheese? It never ends up in the pizzas, right? It just ends up sitting there on your counter, right? Same thing. Whatever reactant is in excess never reacts, but it's still in the reaction mixture at the end. So at the end of a reaction, you're going to have your product plus whatever leftover reactants you have. Just like when you make pizza, you're going to have your product plus whatever leftover reactants you have, right? Whatever leftover ingredients. It's exactly the same thing.
Wait.
It's not any more complicated than this.
Wait, why isn't that shown in, I guess, like, I guess, is there like some sort of equation that shows that the excess will be part of the product, or do you only like figure that out if you like solve something like this?
So, okay, I think what you're confusing is the chemical equation with, so I think what let me put it back to the pizzas. I think you're confusing a recipe for an actual instance of carrying out that recipe.
Yeah.
Here's the recipe which gives you the relationship between ingredients. You may carry out the recipe one day and have 10 crust and 2 cups of cheese, right? You might carry out the recipe another day and have a different ratio of ingredients, right? So in a chemical reaction is exactly the same, right? You may have a chemical reaction like this where you have 15 kilograms of hydrogen and 15 kilograms of nitrogen. Another day, you may have different amounts, right? In which case the limiting reactant would be different based on those amounts, right? But but the equation is the ratio that has to be present that in order for the reaction to occur, because in this equation, mass is balanced, right? You got to have the same amount of mass on this side as you do on that side, because that's the only way the reaction can work.
So in those two drawings that you have, so first you have, I guess, was it the red as nitrogen?
Yeah, no, the red is hydrogen.
So okay, the red as hydrogen and the black as nitrogen. So in the final product, you have NH3, which is the combination of the red and black, but you would also have some excess hydrogen, so you'd have some extra red dots on the...
Exactly, yeah, the extra hydrogen left over, but all of the nitrogen was used up. Why? Because the nitrogen is the limiting reactant.
Okay, I got it now.
Does that make sense?
Yeah. Okay, thank you.
Yeah. This answer is not correct. Sorry, hold on. Let me correct that again, just for the sake of having that right. It should be. This answer is not correct. It should be 1 point. It should be B. It should be this one.
Wait, I got one more question. Sorry.
Yeah.
Will the state of the excess hydrogen be the same as the state of when it was a reactant? So like, in this case, will the excess hydrogen still be, I guess, in the same state as it was when it was a reactant?
Yeah, these are gas, and it will be in the same state. Yep.
Okay.
Yeah.
I guess I'm just thinking about it as like if you mix like baking soda and vinegar as like the product, how it'd be like a semi like.
Very good. So that's a reaction that occurs in solution, right?
Uh-huh.
And so we'll be looking at that in the next chapter. So
okay,
you're one step ahead of me. Taylor, do you have a question?
Yes. Is there any way to figure out the excess?
The
Like
amount.
Yeah, the amount of excess you'll have.
Absolutely. Great question. Let's see. How would you figure out the amount of excess pizza crust that you'd have in this here?
Oh, would you get the excess you would have in the non-limiting reactant and then compare that to the limiting reactant?
Exactly right. So you'd say, okay, I have enough tomato sauce to make 3 pizzas. How many crusts does it take to make 3 pizzas?
3 crusts.
So how many crusts are going to be left over?
It would be 1 crust then.
1 crust, right? So how would you do it here? You'd say, okay, how much ammonia did I actually make? 1.82 times 10 to the 4 grams, right?
Mm-hmm.
So how much of the hydrogen is needed to make that much ammonia, right? How much of the other reactant is needed to make that much ammonia? Figure that out, and then subtract it from this, and that'll tell you the amount that's left over.
Okay.
Just like the pizzas.
So kind of working backwards a little bit on that. Okay, cool.
That's right. Great.
Thank you.
Great question. You'll get some practice on doing that on the problem set. All right, good. Let's see a couple more questions here. Diana.
Is the limiting reactant always going to be the theoretical yield?
Well, no, the limiting reactant, remember, is the thing that determines the theoretical yield. The amount of product made by the limiting reactant is the theoretical yield, yes. But the limiting reactant is not the, right? I mean, so the limiting reactant, right, always determines the theoretical yield. But it's not, it's not the same as the theoretical yield, right?
Right, okay.
Yeah. But yes, the limiting reactant always determines the theoretical yield.
Okay.
Good. I get everybody's questions. Alexander, do you have a question?
Yeah. So I was a little bit confused with, I think, one of the previous homework assignments, which was I was given all the reactants masses in one of the products masses, and it didn't specify for which I had to solve for, but it just said like what's the percent yield, I think, and I wasn't sure what to compare everything to.
So yeah, so you probably had to find, the first thing you would have to do is take those 3 reactant masses, figure out which is the limiting reactant, figure out how much product can be made from that, and then compare that to the actual yield to get the theoretical yield, to get the percent yield, sorry.
Okay, so the theoretical yield is just how much is given of the product?
The theoretical yield is how much you can make based on the limiting reactant.
Okay.
And the actual yield is what's given in the problem.
But even if they don't, even if they don't specify for what element or what part of the formula you're finding.
Right. So it's a problem like this where it has 3, right? Notice in this case, I told you how much it produced of nitrogen, right? So you should do it in terms of nitrogen then, because that's going to be the easiest. Even though the theoretical yield for nitrogen, even though the limiting reactant for nitrogen is always going to be the same as for everything else, do it for nitrogen because that's the one where you ultimately have to figure out the percent yield for.
So it's just, you're just comparing, like finding the limiting reactant, not anything in the product side, right?
Well, again, I think the best way to find the limiting reactant is to figure out which one of those 3 materials, right, that you're given produces the least amount of product. So when you do, you gotta pick a product. Pick the one that you're also given here to figure out the percent yield, right? Because that'll just make your work less. In other words, you can figure out what the limiting reactant is using copper as a product, right? But then once you figure it out, then you're gonna have to go back and calculate again. Okay, well, given that, you know, copper oxide is a limiting reactant, how much nitrogen can I make from that, right? So just pick the one. But anyway, we can talk about this more after class if you like.
Okay.
All right, good questions. Any other questions? Okay, just one other topic left in this chapter, and that's really just combustion reactions, and you've already seen some examples of this. But in a combustion reaction, right, you normally have some substance reacts with oxygen, right, to produce products that are typically the oxides, produce products that are oxides, right? So the typical, the type of combustion reaction that I want you to be familiar with is the type where you have some compound like, let's say, methane or methanol, right, reacting with oxygen. And the products, in this case, if you have carbon and hydrogen, the products are always going to be CO2 and water. In other words, the oxide of carbon and the oxide of hydrogen, right? So the type of problem I expect you to be able to solve is something like saying, okay, write a combustion reaction for the combustion of C2H6, let's say, right? So how would you do that? You'd say, okay, I know what a combustion reaction is. When I have carbon and hydrogen, it's going to combine with oxygen, and it's going to form what? CO2 plus water, right? And then I need to balance that, right? So how would I balance this? I'd say, oh, okay, I have 2 carbons here, so I'm going to put a 2 there. I have 6 hydrogens. Notice I'm going to save oxygen for the end. Why?
Because it's a lone element.
It's a pure element, right? And you're always going to save pure elements for the end. So I'm going to balance carbon first, and then I'm going to balance hydrogen. I have 6 hydrogens over here, so if I put a 3 over there, that gets that balanced, right? And then now I save this for the end. I got 3 and 4, right? 2 times 2 is 4, 7, so I need a 7/2 here, right? And then finally, I want to clear that fraction, so I want to multiply everything by 2. So that's 2. That becomes 7. That becomes 4. And that becomes 6. And there is a balanced combustion equation for C2H6. Okay? That's all I really want you to be able to do in terms of combustion reactions. Okay? I want you to write balanced equations for that.
How did you know that the products are CO2 and H2O?
Whenever it's combustion, whenever you have combustion of a hydrocarbon, carbon, hydrogen, the products are always going to be CO2 and water.
Okay.
Okay, so you just have to know that. Emily?
That was also my question.
Okay, yeah. So
because if it's not a hydrocarbon, we can get other oxides as
correct. So the only other ones that I won't ask you about these, but the other ones are things like if it has nitrogen, then nitrogen shows up as NO2. If it has sulfur, sulfur shows up as SO2. All right, but don't have to worry about those. Mostly just carbon, hydrogen, oxygen form CO2 and water, and then balance the equation.
Got it.
Okay. Let's see. Any other questions on this? Okay, great. I have a few extra minutes, so I'm going to just introduce our next topic. So give me 1 second here. All right. Our next topic is going to be solutions and reactions in solution. Okay. So I'll just tell you a little bit about this. This is it's called a spherified cherry. How many of you ever seen something like this? Anybody? So this is a product of something called molecular gastronomy. All right. So molecular gastronomy is kind of a technique where you marry chemistry and cooking, right? And you can tell from my background of making pizza from Cheese Whiz that, you know, this is right up my alley. No, actually, I actually really like to cook, believe it or not. And I don't use Cheese Whiz anymore, I promise. So I've actually made these creations because it's a combination of two things I love, chemistry and cooking. And essentially what it is, it's whatever juice you want or whatever liquid you want to encapsulate, you can encapsulate in this kind of edible membrane, right? So it's a way to turn liquids into kind of an edible little solid, right? And so you pop this thing in your mouth and it kind of bursts, and it's super interesting. This style of food was made famous by, well, one of the chefs anyway that helped make it famous is a chef named Jose Andres, and he's a Spanish chef. His family is actually from northern Spain, a little town in the province of Asturias, which is where my grandfather is from. So I kind of really like Jose Andres, and I like what he does. And so he does a lot of this molecular gastronomy. So I've been to a couple of his restaurants and tried this kind of stuff. And then I try to make it myself, right? So you can do, this is a spherified cherry. This is actually a spherified olive, right? And the way you make this is kind of fun. So you make a solution. You kind of like take you either take cherries and mash them up and extract what comes out, or you take olives and mash them up and extract what comes out. And then you make a solution that contains sort of the olive juice, if you will, right? In a substance called calcium chloride, okay? Oh yeah, who made the mojito sphere there? Emmanuel. All right, yeah, I made those as well, but I didn't want to say that to you guys. You guys are too young to drink mojito spheres, I guess, right? No, not all of you, but some of you might be. All right, anyway, so you mix up the olive juice with the calcium chloride, right? And then you have the solution that kind of looks green, right? And that green solution of calcium chloride and olive juice, you pour into another solution of sodium arginate, okay? And here's what happens. The calcium from the olive solution that you're pouring into here forms this solid with the arginate ion over here. And this is called a precipitation reaction, okay? And that's one of the things we're going to be looking at in this chapter is precipitation reaction. So you got the calcium that's mixed with the olive juice with the arginate that's in this bath, but where are they both together? Only at the outer border where they both meet, right? Because over here, you don't have any calcium, right? And here, you don't have any arginate, right? They're only both present right at the border, yeah? So right at the border, you get this solid that spherifies this liquid, right? And you get your olive, right? You get your spherified olive. Anyway, it's super fun, and too bad we didn't have class. We could make them and then eat them. Okay, so that's what this chapter is kind of about. We're going to look at solutions and reactions in solutions. All right. So we got to start with a few preliminary things, looking at the concentration of solutions. And understanding how to specify that. And then we're going to look at solution stoichiometry, which just takes the same principles we just learned, right? But but applies them to reactions in solution, all right? And then we'll look at different types of solutions, and then we'll look at these precipitation reactions, which are the reactions that produce these great things right here, all right? So let's see, I have 5 minutes. Let me just introduce a couple of terms, and then we'll call it a day, all right? The terms I want to introduce, the first one is the term solution, all right? Solution is a homogeneous mixture of two or more substances. All right, a homogeneous mixture of 2 or more substances. So remember we talked about mixtures before, homogeneous versus heterogeneous, right? So a solution is just a homogeneous mixture of 2 or more substances. For example, salt water is a solution, right? Salt and water. Sugar water is a solution, okay? The air around us right now that you're breathing is a solution. It's pretty much a homogeneous mixture of nitrogen and oxygen, right? Vodka is a solution, right? It has water and ethanol in it. It's a homogeneous mixture of 2 substances, right? So solutions can be mixtures of gases, of solids and liquids, of liquids and other liquids, right? It doesn't matter what the state is, but it just has to be a homogeneous mixture of 2 or more substances. When you buy carbonated water, that's a solution, right, of carbon dioxide and water. When you open it, right, the carbon dioxide comes out. But while it's pressurized, it's a homogeneous mixture of the 2 substances, right? So those are all examples of solutions, all right? Let's see, a solution has 2 components. The solute, which is normally the minority component, and the solvent, which is usually the majority component. Right, so when you have a solution of salt water, yeah, sodium chloride is the solute and water is the solvent, right? Okay, an aqueous solution is a solution in which water is the solvent, right? So if you can have different kinds of solutions because you can have different kinds of solvents, but an aqueous solution is what's in which water is a solvent. And these are the most important type of solutions that we're going to really focus on these. Why? Because water is all over the place. You know, basically our bodies, our blood, the composition of our cell, the fluids inside our cells are all aqueous solutions. So these are one of the most important types of solutions. So we'll really focus on aqueous solutions, but know that it doesn't have to be water as a solvent. There's a lot of different kinds of solutions out there besides aqueous solutions. Okay. All right, folks, it's 3:20. Thank you for your attention today, and thank you for coming. And I'll look forward to seeing you all on Wednesday. Don't forget my office hours if you need help. Go see the TAs if you need help, and just keep going. Don't fall behind. Most of you are doing very, very well. And I'm so happy about that, and I want to see you keep it up. So thank you so much for your attention. Have a great day. I'll stick around for anybody that has questions. Bye.
Thank you.
Thank you.
Thank you, Professor.
Thank you.